All right, this is the lecture on choice modeling. We're going to get into the theory of how we build models to predict people's choices. So, as a starting point, let's do a quick review of probability concepts. Let's say we have a random variable x, and we put a little squiggly line over it to denote that this is a random variable, meaning the value of it is subject to variation due to random change. So think of the outcome of rolling a dice. If we called that value x, then it's going to be different depending on every roll. Now, random variables have certain properties. One of them is they have a probability density function associated with it, a PDF. So this is the PDF of a standard normal distribution. And the way you read this is the y-axis tells me the probability of any of these values x occurring. So the value 0 is about 0.4, meaning this is the highest probability value is 0. And as we get away from 0 on either side in this particular distribution, the probability gets lower. So it's a much lower probability that this value is going to be negative 2.5 or 2.5. One other thing we can do with probability density functions is we can use integration to compute the probability of x being between some value. So if we want to know the probability that x is between a and b, then we just integrate under this curve. We compute the area under the curve of the PDF, and if you remember from calculus, that's just an integral. So we're integrating from a to b of the probability density function f of x. Now, if all this sounds like a lot, don't worry. It's basically all we're trying to do is say it's about the area under the curve. Another function that's useful for us is the cumulative density function, or the CDF. So the CDF is saying, what is the probability that x is less than or equal to some value x? So in this case, if we want to know the probability of a value being less than a, then we're integrating the PDF from negative infinity up to point A. Okay, so you can read this off by looking at values like, let's say x is 0. Well, the cumulative distribution function is at 0.5. So that means that there's a 50% chance that the value of x is less than or equal to 0. Likewise, if we go all the way up to 2.5, it's really high. So there's a really high probability that x is less than or equal to the value 2.5. These are two functions that we're going to use later on. You can also have multivariate distribution. So if you have multiple random variables, in this case x and y, then you might have a joint distribution that's going to tell us the probability of the values x and y simultaneously occurring. Now in this case, this is a three-dimensional PDF, and you can have really an infinite number of dimensions here as we increase the number of variables. And another important concept is the concept of independence, which means that random variables are independent of each other if the value of one doesn't affect the other's probability. Now, one convenient thing that we can do if we have independent variables, then we can compute their joint distribution by just multiplying their individual distributions. So if we know the distribution of x and we know the distribution of y, then their joint distribution is just the multiplication of these two things. And that's a really convenient feature, and we'll end up exploiting that again later. So let's do some practice questions on probability. Part A is a random variable x has the PDF f of x. Write out the equation to compute its total probability. Now here, think about the total area under the curve. That's what we're trying to compute. What would the answer to this equation be? Part B, a random variable x has a uniform distribution between the values of 0 and 1. Draw the PDF and the CDF of this variable. And C, the random variable x is determined by rolling one fair six-sided dice. Draw the PDF and CDF of this variable. Now we're going to get into random utility theory. We use utility theory to model people's preferences. A utility is this concept that refers to the satisfaction someone gets from a certain product. Utility is a random variable. So remember, we're going to denote this with the little squiggly line over the U, and that's the notation we use for random variables. Now I use a subset J here. That is referring to the product J from a set of products. So usually you have multiple products that you're making a choice from, and you're going to compare their utilities. Utility has a relative value, not absolute. We can only really compare the utility of one product to another, and it doesn't have any units. This is not a really concrete concept. It's pretty abstract. It's just a numeric value that it can be used to compare relative to other alternatives. So let's have a concrete example here. We have three phones. They have different prices, battery life, and signal quality. Phone 1 has the lowest price, best battery life, and the best signal quality. And phone 3 is at the opposite extreme. It's the most expensive, worst battery, worst signal. Phone 2 is in between. So in general, we would assume that the utility for phone 1 is higher than that of the other two, and the middle and 2 is also higher than 3, because it has the preferred attributes that we would logically want: lower price, better battery life, and better signal. Utility can be broken into two parts, an observable part and an unobservable. We use V sub j to denote the observed utility. In that last example, this would be things like the price and the battery life, and the signal quality of the cell phones. The epsilon refers to an error term. These are things that we may not be able to measure, and we assume that it's a random variable that has some variance but a mean of 0. So visually, I like to think of it this way. My utility, total utility for this alternative j, is the summation of the observed utility, which might be some fixed number, plus my random term, the epsilon. Now, the random term has a mean 0, but it does have some variation, some variance. Okay, so overall, the utility becomes a random variable because of this error term. We're going to assume that a consumer is going to choose a product if it has a greater utility. But keep in mind that because utility is a random variable, the only thing we can really compute is the probability that the utility of one alternative, j, is higher than that of another alternative, k. So let's think about some different examples. What if our utility distributions looked like this? Well, in this case, the utility for product k is higher than that of utility for product j for most of the time. There's very little overlap. So the probability I'm going to choose this lower one, j, is pretty low, maybe even 0, or almost 0. Here, the PDFs overlap entirely. They're exactly the same. So then the probability I'm going to choose j over k is just a coin toss. It's a 50% chance. Here, u of j is a little bit higher, and so the probability here is getting closer to 1. It's 0.75. And in this case, I'm at the other extreme where I'm almost always going to choose j over k. To compute the probability that consumers are going to choose one alternative or the other, what we want to know is the area under this joint distribution. So this involves integration again. So probability of u of j is greater than u of k can be broken into these components, the parts that we can observe, vj and vk, plus the parts we can't observe, the random error terms, epsilon j and epsilon k. We can move these terms around, and we see that really what we're trying to solve here is, once we account for the difference in the things we can observe, it's just the probability of epsilon j being greater than that of epsilon k. When we turn this into integration, it becomes a really messy equation where we have to do a double integral over the joint distribution, this f term here, f of epsilon j and epsilon k. To answer this, we have to know what the joint distribution is. And so we have to make an assumption about what these epsilon terms are. There are a few different options for choosing a distribution for epsilon. A normal distribution produces a model that's known as the Probit model. And the advantage of this is that there's a lot of theoretical reasons why this might be a good choice. But the disadvantage is that there's no closed form solution. That really nasty integral that we would have to solve gets even nastier when you put in a normal distribution for the joint probability distribution function. So another option is known as the Logit model, where we use a type 1 extreme value distribution. Now, this extreme value distribution is one that's not often used in other contexts. Not many people are familiar with it. But when you compare it to the normal distribution, it looks like this. So it has a similar median point as the normal distribution, but it's slightly more skewed to the right. So we use it really as an approximation to the normal distribution, but it also gives us a lot of convenience. And one of the main things it provides is it results in a closed form solution for those probabilities. So remember, if we want to compute the probability of choosing j over k, we have to solve that huge integral. But when you input this distribution, that all breaks down to a simple fraction. Now this might still look a little complicated, but let's break it out for a specific example. Let's say we have two alternatives, j and k. Well, then the probability of choosing j is e to the vj over the sum of e to the vj plus e to the vk. And for the probability of choosing k, it's just the opposite. So you see the denominator is the same. All you really have to do is compute what's my observed utility for j and what's my observed utility for k. You exponentiate those, and then you can do a simple fraction to get one and a simple fraction to get the other. Now, this does have some drawbacks. One is that the errors have to be independent. That is a key assumption of this model, and in the next slide I'm going to talk about some of the limitations of that. But this is going to be the model we're going to use for this class. The independence of irrelevant alternatives property it's a mouthful, but the IIA principle really becomes problematic when your products are very close substitutes. It means when you have multiple alternatives that are really similar to each other. Let me illustrate why this becomes a problem. The classic example is the red bus versus blue bus example. Let's say you're at the airport and you're trying to get somewhere really fast, and so your alternatives are a taxi or a red bus. And the bus you know is going to be a little bit slower, you're not super sensitive to price, so your utility for the taxi is a little higher than that of the bus. So let's just say that the E sub Vj is 2 for the taxi and 1 for the bus. Well, if we want to compute our probabilities, remember this equation, all we do is we say the denominator is the sum of these two, so it's 2 plus 1 on each side, and the numerator is 2 for the taxi and 1 for the bus. So this results in 2/3 of the time you would choose the taxi and 1/3 of the time you would choose the bus. Now let's say we added a third alternative, a blue bus. Well, what we would expect is that the color probably really doesn't influence our decision here. So we would expect our probabilities to probably still be the same, that at least around 2/3 of the time I'll still probably take the taxi, and these buses are probably just going to split the share of the red bus. So each of them are going to get half of this 0.33. That's what I would expect to happen, but let's look at what happens with the Logit model. Because these two alternatives are virtually the same, I'm going to assign them the same utility here. So e to the vj is 1 for each of them. Well, then my probabilities become 0.5 for the taxi and 0.25 for each of the bus. So what the Logit model is doing is it's pushing some of the probability over to each of these alternatives, the red bus and the blue bus, and the taxi is now being brought down to 0.5. So it's really underestimating what the real probability would be for choosing the taxi. And in reality, I should probably just model these bus alternatives as the same alternative, just one bus. So if you're running a model where you have choices between alternatives that are very similar, that's where IIA becomes a problem. Okay, so let's do another practice question. Let's say a consumer is making a choice between two bars of chocolate. You have a milk chocolate bar denoted with an M and a dark chocolate bar denoted with a D. Assume that we know the observed utility to be V sub M is 3 and V sub D is 4. Now, using a Logit model, compute the probabilities of choosing each bar. As a hint, remember the probability equation for the Logit model. Now for part B, let's assume that we've added a third bar of chocolate to the choice set. It's exactly the same as the milk chocolate bar, but it has a slightly different wrapper, which has no effect on your consumer's utility. So VM1 and VM2 are the same, they're both 3, and V sub D for the dark chocolate is 4. Based on the probabilities from the part A, what would you expect the probabilities to be for choosing each bar? And then compare that to what probabilities does the Logit model actually produce. Now, up until now, I have been referring to the observed utility, V sub j, as just some number, something that we somehow know. But what we really want is to be able to compute that number based on observable attributes, x sub j. So this is going to look like something like this, where we're going to have a series of weighting values, betas, beta 1, beta 2, and so on, and a series of our attributes, x1, x2, and so on. So in our phone example, let's say we have price, battery life, and signal quality. In fact, I had these pictures before. Let's give them actual numbers. So now we have battery life in terms of hours, signal quality in terms of percentages. Let's call it percentage of reception. And so our x's are going to be x1 is price, x2 is battery life in hours, and x3 would be signal quality. So if we want to compute the utility, the observed utility for phone number 1, we're going to take that price value times beta 1 for price, plus the hours on battery times beta 2, plus the signal quality times beta 3. That is our observed utility for phone number 1. For phone 2 and phone 3, we're going to compute them the same way, inputting these values for the phones. So here we don't know what these values are, beta 1, beta 2, beta 3, and in the next lecture we're going to talk about how we estimate these values. But for now, we're just talking about how we construct a model and what these values mean. So let's say we've built a model and we estimated that these are the coefficients of our model. Beta 1 is this negative 0.01. Well, then what would this mean? Well, this means that if we go from phone 1 to phone 2, we're increasing the price by $100. So 100 times 0.01 is 1. So that means this is a negative coefficient. So that means when we increase the price by $100, our observable utility goes down by a value of 1. All right, and that would make sense, right? We don't like to pay more for the same thing. So if you increase price, utility goes down. Likewise here, a positive 0.1 times your battery life in hours means if you increase my battery life by a factor of 10 hours more, I gain utility by 1. So if we computed the observable utility for each of these phones, it would work out like this. It's basically a simple sum product. And we get 5, 2.5, and 0. Now what does this mean? Well, these only have, remember, relative value. It doesn't mean that phone 3 has no utility. Having a value of 0, that's not what it means. All we can say is that phone 2 has 2.5 more than phone 3, and phone 1 has 2.5 more than phone 2. It's a relative scale that tells us the observable utility for phone 1 is the highest, and the observable utility for phone 3 is the lowest. So again, these are weighting factors that we're going to try to estimate. We're going to learn how to estimate them later, but for now, I want to get across the point that this is how we would build a model to describe the observed utility. It's a function of weights times the different attributes. Now there are different types of attributes. In this past example, all of these attributes were continuous. And by that I mean that they can vary along a continuous scale. So dollars can go anywhere from 0 to infinity. And so when we're modeling this with different beta coefficients, well, these coefficients are telling us the slope of a line. It's saying as you increase one continuous variable, this is how utility changes. So let's visualize this for just signal quality, beta 3. If we were to plot this, it would look something like this, where as we go from a lower signal quality to a higher signal quality, the change in my observable utility is going to go up by some amount. That value, the slope of this line, is what beta 3 is. So if I had some other phone that had a signal quality of something in between, let's say 70, I could compute for you what the difference between 70 and 60 is. It would just be 10 times beta 3. But you can also have these categorical or discrete attributes. So now let's look at signal quality as if it was defined with just 3 discrete values, low, medium, and high. How would we construct that utility model? Well, the way we would do that is we would add dummy coefficients into our model. So the price and battery life coefficients are the same. These are still continuous variables. But now you're seeing that we have this new variable, a delta with a medium and a delta with a high. These are dummy coefficients, and what that means is they're either going to take a value of 1 or 0. If my phone, let's say phone 2 has a signal quality of medium, then the delta here is going to be 1 and the delta here is going to be 0, which means this whole term is going to drop out. Likewise, for phone 1, it has a high quality, so this one's going to be 0 and this one's going to be a 1. So it's only going to get a contribution from beta 4. Now you'll notice that there is no delta for low. Why is that? Well, Because utility is only a relative concept, you can only have utility relative to another value, you have to choose a baseline value when you have a discrete or categorical attributes. So for here, we've assumed low, the category of low signal quality, to be at the point 0. So what beta 3 is going to tell us is what is the discrete increase when we go from low to medium. Likewise, beta 4 is going to say what is the change in utility when we go from low to high. So to visualize this, you're looking now at an x-axis that has 3 discrete levels. If low is the 0 value, then beta 3 is saying what is the discrete increase from low to medium, and beta 4 is saying what is the change in utility when we go from low to high. So we can take care of attributes that have discrete values. We can still manage them in this modeling framework. They don't all have to be continuous. And we're going to talk more about the difference between continuous and discrete attributes later. So for our last set of practice questions, let's say we're making choices between 3 different bars of chocolate. We have prices and we have percentage of cacao. So this is a darker bar and this is more like milk chocolate. Question A, write out a model for the observed utility of each chocolate bar in the above set. Now remember, this is just the observed utility, the V sub j. In question B, let's say the coefficient for price was negative 0.1 and the coefficient for the percentage of cacao was positive 0.1. What is the difference in the observed utility between bars 3 and 1? Now we've added the brand attribute. We have Hershey's, Lindt, and Ghirardelli. Repeat part A, so write out the model of the observed utility with the addition of the brand attribute. Now keep in mind, these are discrete attributes.